Hello everyone. I welcome you all in our YouTube channel Engineering Shiksha. So this is fourth lecture in on network series, and today we are going to discuss transient in RL and RC circuit. So this lectures contain generalized solution of first order non-homogeneous equation, and we have also solved numerical based on first order differential equations. So target audience for this particular lecture, that is, this lecture is actually beneficial for undergraduate and diploma students of electrical, EC and IC branch for their semester examination. As we also going to solve some previous year gate examination, so this is also beneficial for all those students who are preparing for gate and as well as other competitive exam. Let's start our lectures. Let us say we are having a first order non-homogeneous equation. So this is the first order non-homogeneous equation. The value of q is not equal to 0, so it is considered as a non-homogeneous equation. If you finding out the order of this particular equation, you can turn out to be a first order differential equation. The first question may rise that, sir, why we require to solve this particular equation and when we require? The answer is that whenever you are solving your RL and RC circuit, when you apply a KVL or KCL, most of the time your equation will be turned out to be in form of dx by dt plus px equal to q. If it is not turned out to be a dx by dt plus px equal to q, you have to take the integration and differentiation, but finally your answer or your equation could be in form of dx by dt plus px equal to q. Remember, when x could be anything, it may be possible voltage or it may be possible current. And when every time you are going to solve the equations, then it could be a lengthy process. So instead of that, what we are doing, we are trying to solve all these steps, and that particular solution that we are obtaining over here, we are utilizing in our each and every example whenever we require to utilize that. So let's start our lecture. Let us say we are considering we are having one equation that is equal to di by dt plus pi equal to q. But remember, right now we are considering the I, but it is not necessary that every time you are having this variable. Maybe possible you also have, instead of I, you are having a v. So this is also applicable for that case also. It means that if I am having the equation that is dv by dt plus pv equal to q, then also you can apply all these steps. Okay. So to finding out the solution, let us say initially I will multiply e raised to pt on both the sides. So I will multiply e raised to pt. Let us mention some name, equation A. So I will multiply e raised to pt in equation A both sides. Right. So what I will get, let me multiply with this. So I will get e raised to pt di by dt plus ei into e raised to pt. If I will multiply e raised to pt on left hand side to make balance, I have to also multiply this on right hand side also. So let me mention here also right hand side. This is e raised to pt. If you remember these rules, if I am having, let us say, d by dt of two variables, okay, that is y into x. If I am having a two variables and I would like to take the differentiation, how I can take the differentiation? I will take initially, let us say, first variable constant, and I will take the differentiation of second variable. And then I will take the second variable constant and I will take the differentiation of first variable. If you observe this equation carefully, this line carefully, this is e raised to pt. It means that you are making e raised to pt constant and you are taking the another variable or differentiation of another variable, that is di by dt. Now in the next case or in the second term, if you observe, your I is constant, okay, and now you are taking the differentiation of e raised to pt. So if you take the differentiation of e raised to pt, you will get e raised to pt, and when you take the differentiation of this power, what you will get? P, that is multiply, right? So it means that this two term is nothing but that is equal to d by dt of e raised to pt into I. So can we write down this? So let us write down this. So it means that I can say that if I am applying this rule, I will get d by dt of e raised to pt into I, that is equal to q into e raised to pt, right? Now remember what I have to calculate. I have to calculate this variable I. Okay, so to get this variable I can take the integration both the sides. So let me take the integration both the sides. So what I will get? Differentiation on the left hand side, differentiation and integration get cancelled. So I will get e raised to pt into I, right? And if I will take the integration on right hand side, that is equal to q into e raised to pt. That's it? No. You require another thing, that is the integration constant. So let us say k, where k is the your initial condition, or you can say that at time t equal to 0, you are having some constant that is equal to your integration constant. But when you take a reverse side, this, if you take the differentiation of this constant, you will ultimately get 0, right? So this is e raised to pt into I q integration q e raised to pt plus k. What I have to calculate over here, my focus is to calculate this variable I. So let me simplify further. So I will get I that is equal to, if I will take e raised to minus pt on right hand side, so what I will get? E raised to minus pt, right? So let me write down over it. This is e raised to minus pt integration q e raised to pt plus k e raised to minus pt. This expression is very important to solve our first order differential equation. Though I will repeat again, though I have mentioned this is I, but this could be I or this could be B depending on our requirement. So let me write down this expression once again. So this is your di by dt plus pi equal to q. If I am having this type of equation, then I can directly write down the expression for this particular equation, that the variable I, sorry, the variable I in this particular equation, that is equal to e raised to minus pt integration q e raised to pt plus k into e raised to minus pt. So remember, every time you have to remember this equation for solution of first order differential equation. So let me further write down this. Your I can be written as, if you remember your mathematical class, this can be known as, or this can be also referred as I, that is equal to IP plus IC. Okay, this is known as particular solution, or let me write down further this. This can also be written as ISS plus IT. Okay, it means that ISS means your steady state component and IT represent your transient component. Okay, so this is also, you can see that this is your force response, and this is your natural response, right? Force response means this is due to, force response means this is due to supply voltage you are connecting with your RL circuit, and transient response means if I am not connecting any kind of supply voltage, then the response that I can obtain, that is my transient response. So as time goes on, this ultimately goes to be, or this has to be vanished, right? So remember, this part is represent your complementary function, or you can say that the transient response, and this response is your steady state response. Okay, and now we are trying to obtaining this expression. In the last few lectures, what we are discussing, we are only focusing on our initial condition. What could be the value of current at initial condition? What could be the current at final condition? What could be the rate of change of current? Okay, di by dt, d square I by dt, but we never calculate the final expression so that we can calculate the current at any time instant. So at any time instant, you cannot use the initial condition to find out the value of current. But using this particular expression, we can calculate and we can finding out the value of current at any instant. So with this background, this is the, let us say, the steps that we are going to follow our today's example, and as well as all the example that is belongs to our first order differential equation. So as usual, first we are draw our equivalent circuit for t less than 0 minus, and we will calculate the voltage or current as per our requirement. So initially what we are considering, let us say at t equal to 0, there will be some switching. So what we are considering, just before the switching, what could be the circuit condition? So we will draw the equivalent circuit just before the switching conditions. Okay, just before the switching means, let us say if I am doing my switching at 9 am instant, We can consider just few microseconds before 9 a.m. and we will draw the equivalent circuit. We will check whether inductor is short circuit or not, whether capacitor is short circuit or open circuit or not, and we will draw the equivalent circuit. And based on our requirement, whether we have to calculate voltage or whether we have to calculate the current, we can finding out our required value. So this is our first step that we are going to follow. Then in the next step, what we are doing, we are going to draw the equivalent circuit for t greater than 0. So t greater than 0 means after the switching. And again, we apply a KVL, KCL and node voltage analysis depending on our requirement. Most of the time when we want to finding out the current, we will apply a KCL, and whenever we have to finding out some node voltage or voltage across the capacitor, then we are applying KCL, and KCL should be combined with node voltage analysis. So this is the second step that we are going to follow to finding out our first order differential solution of first order differential equation. Then after that, whenever we are applying the KVL and KCL, we will get the solution or we will get the expression that contain the first order non-homogeneous equation. So we will use our generalized solution that we earlier derived, and we will utilize that generalized solution and finding out the solution. After doing this, whenever we are applying generalized solution, we will find out one term that is known as the constant K term. So that generalized solution, finding out a particular solution, what we require to calculate the value of K. So what we are going to perform here, we are calculating K value by considering the initial condition. It means that we are considering, let us say at t equal to 0, what could be the variables or what could be the value of current or what could be the value of voltage. So based on value of t equal to 0, we will put in our generalized solution. We can find out the value of current or voltage based on our initial condition. So by using these two, generalized solution and initial condition, we can find out our constant K, and that is our particular solution. So with this, let's start our today's example. So in the network of figure, steady state is reached before switch K is closed. Okay, so it means that I have one network. In this network, switch K is closed at time t equal to 0. It means that I am closing this switch at time t equal to 0. So let me mention over here, this switch K is closed at time t equal to 0. And it is also mentioned that the steady state is reached. What do you mean by steady state is reached before the switch is closed? It means that my inductor is right now at situation that is equal to t equal to infinite. Let us try to understand with some example value. Let us say I am closing this switch at, let us say, 9 a.m. Okay, I am closing this particular switch at 9 a.m. But I have connected this circuit very earlier, maybe possible 8 a.m., 7 a.m. So let us consider some value. Let us say I am considering 7 a.m. At 7 a.m. when I am closing this switch, maybe possible at that time inductor will behave as a open circuit. Then inductor start charging. And 9 a.m. when I am closing this switch, okay, when 9 a.m. I am closing this switch, inductor already charged. Okay, and that's why I have mentioned over here, this for inductor it is t equal to infinite situation. Always you have to remember this thing, that your t equal to 0, that is the switch close time, that is not equal to t equal to 0 for inductor. You have to read your example carefully. It is given that steady state is reached, right? So before the switch key is closed. So it means that, let us say 9 a.m. if I will close the switch, so just few microseconds before 9 a.m. Okay, just few microseconds before 9 a.m. So it means that there will be a, let us say, 8:59 and some, let us say, 90, right? So this is the situation. If I am considering, let us say, 1 minute before. Okay, so 1 minute before, what is the situation? So we have to always consider some microsecond before only. Anyway, so this time, what is the situation? That your inductor is fully charged, and if inductor is fully charged, it will behave as a short circuit. Always remember, when inductor fully charged, it will behave as a short circuit. When capacitor fully charged, it will behave as a open circuit. I remember this point so many times. Never confuse with time t equal to 0. Switching time t equal to 0 with your inductor charging time t equal to 0. Okay, at 7 a.m. when you are connecting this circuit first time, at that time your inductor will behave as a open circuit, T equal to 0. So now let me draw the equivalent circuit at time t equal to 0. So at time t equal to 0, I should mention over here, this is my circuit at time t less than 0, just before the switching. So just before the switching, this switch is open. So I have not draw this circuit because this is ultimately open circuit path, right? And this inductor will behave as a open circuit. So what is the situation? Let me mark the current which are flowing this through this circuit. Okay, that is I0 minus. So previously, if I want to calculate the current which actually flowing through this particular circuit, that is equal to. So this is very simply you can calculate. This is 20 volt and this is 10 volt. It means that these two voltage source are connected in series, so total voltage that is 30. Now let us calculate the resistance of this particular circuit. So your total resistance is 30 ohm plus 20 ohm, so that is 50. So total resistance is 50 ohm. So 30 into 50, okay, 30 divided by 50, or you can say that this is 60 divided by 100. So you can say that current that is flowing through this circuit, that is equal to zero point 0.6 ampere. So it means that current flowing in the circuit that is equal to zero point 0.6 ampere. This is the situation that is just before the switching. Okay, so at 9 a.m. or just few microseconds before 9 a.m., if I am going to measure the current, okay, that is flowing in this particular circuit, then that should be equal to how much? So that should be equal to zero point 0.6 ampere. Now let us consider what could be the situation at time t greater than 0. So at time t greater than 0 means what? You have to observe. Let us say at time or at 9 a.m. you are doing your switching. And now we are considering after 9 a.m. Just few seconds after 9 a.m. What is the condition? You close this circuit, right? When you close the circuit, your equivalent circuit could be look like this. Okay, so this is your circuit. Now you have to apply a KVL. So let me draw circuit over here again. So this is my circuit, right? So what I have to calculate over here, I have to calculate the current which are flowing through this inductor. So it means that I want to calculate. So maybe possible you can apply a KVL in this particular loop also. But to simplify version, I will use this loop. Okay, so this is the loop I'm going to apply so that I will get the solution. So let me start with this. So we will start with this point 20 ohm. So I'm having, let us say, 20 ohm resistance, and that is multiply with current I plus. What about the voltage drop across the inductor? So it is L di by dt. So value of L is given, that is 1/2, and current value that is di by dt minus 10. So if you take minus 10 on the right hand side, then it is equal to plus 10. So we never require this particular part of the circuit. Okay, so this is not important for us. So remember, if we are having an equation that is di by dt plus pi, that is equal to q. So my equation should be this in this form. It means that di by dt should not have any multiplication factor. So to finding out this solution, let us multiply this equation with 2. So what I will get? This 1 by 2 multiply with 2. So I will get 1. So this is di by dt plus. If you multiply 20 into 2, so this will become 40i, that is equal to 20, right? I have just multiply with 2 to get this kind of solution, that is di by dt plus pi equal to q. So now if I am comparing these two equations, then what I will get? The value of p, that is equal to 40, right? And what is the value of q? That is equal to 20. Now you must have to remember the solution of this equation. If you don't require or if you don't remember this equation, then it could be finding out, or it could be difficult for you to calculate the solution. So for right now, I will just write down this expression. So this is your expression, that is I is equal to e raised to minus pt integration q e raised to pt plus k into e raised to minus pt. So it means that I, that is equal to e raised to minus, what is the value of p? That is 40. So let me write down here, that is 40 into t. Then integration q, value of q is 20 into e raised to 40t plus k e raised to minus 40t. Let us further simplify this. This is e raised to minus 40t. 20 is constant, so take out of integration. Now integration of e raised to 40t. So you will get e raised to 40t. This is the integration of e raised to x. Now let us integrate this power. So you will get divide by 40 plus k e raised to minus 40t. Okay. So e raised to minus 40t and e raised to 40t. So that is equal to 1. 20 divided by 40. So that is 1 by 2. So this is 1 by 2 plus k e raised to minus 40t. This is my expression for current. Okay. This is known as generalized solution. Okay. Because you have right now not finding out the value of k. So if in exam they mentioned that you have to obtain the generalized expression, then you have to solve your example up to this point. But if they have asked you finding out the expression for current, or if you have to finding out or calculate a particular solution, in that case you have to also calculate the value of k. And how to calculate the value of k? We have to consider initial condition. Okay, so now let us consider initial condition. So now let us say at time t equal to 0. So let me put or let me mark or this equation as, let us say this is my equation number p. Let us say at time t equal to 0. So I will put the value of t equal to 0 in this equation. So current I, that is also I can say that is I0. So this is the current I of 0 that is flowing at time t equal to 0. That is exactly at 9 am. That is equal to 1 by 2 plus, okay, put the value of e raised to 0 in this equation. So what I'm getting, e raised to 0. Okay, so e raised to 0 is 1. So that is k into 1. So it means that I of 0 that is equal to 1 by 2 plus k. What is the value of current at time t equal to 0? We already calculate current I of 0 at time t equal to 0 in our previous slide. I of 0 that is equal to 0.6 ampere, right? So it means that at time t equal to 0, current flowing through inductor that is equal to 0.6 ampere. We have calculated the current just before the switching, but we know that at inductor case, just before the switching, at the time of switching, and just after the switching, current flowing through inductor will remain same. So it means that just few microseconds before the switching, okay, just few microseconds before 9 am, at 9 am, and just after 9 am, just few microseconds after 9 am, the current flowing through the inductor that is equal to how much? 0.6 ampere. So if I will put here 0.6, this is 0.5. So it means that value of k that is equal to 0.6 minus 0.5. So that is equal to 0.1. So let us put the value of k equal to 0.1 in expression b. So I will get I that is equal to 0.5 plus 0.1 e raised to minus 40 into t. This is known as your particular solution for this circuit, right? If you observe this expression, what we are doing, we are finding out the expression of current. Now if you are having a value of t, let us say 0.1 second, 0.2 second, 0.1 microsecond, you put the value of t in this particular equation, what you will get? You will get your final answer. Okay, let me plot this curve so we will get further some more idea. Let us say I that is equal to 0.5 plus 0.1 e raised to minus 40t. This is the expression that we derive. Let us put the value t equal to 0 in this equation. If you put t equal to 0 in this equation, what you will get? Your I of 0 that is equal to how much? Let us say 0.6 ampere. So let us say this is the point 0.5 and this is, let us say, you can consider a 0.6. This is my time axis. So let us say this is the point at time t equal to 0. So at time t equal to 0, current is flowing through this circuit. Okay, just before the switching also 0.6, just after the switching also 0.6. Okay, let me put the value t equal to infinite in this equation. If you put e raised to infinite t equal to infinite in this expression, what you will get? E raised to minus infinite. That is equal to 0. So it means that I at infinite, that is equal to how much? 0.5 ampere. So it means that initially my current is 0.6 ampere and it will start decreasing. Okay. And it will start decreasing. So if I will draw or if I will plot this, I will get this type of expression. And finally it will reach to a zero point 0.5. Okay. This is your 0.5. So this is my plot of inductor current. This is my plot of inductor current, and finally it will be reached to a steady state value that is equal to how much? 0.5 ampere. So remember, this is my point at time t equal to 0. For our case, this is 9 a.m. right? Just before the 9 a.m. current flowing through inductor is 0.6. Okay, just after the 9 a.m. current flowing through inductor is 0.6. Okay, just before and just after. In both the case, current flowing through inductor is 0.6. Then current flowing through inductor is gradually decrease. Okay, and at t equal to infinite, this point we can consider as t equal to infinite. At t equal to infinite time, this will depends on what? Your time constant. Okay, so this is your generally 5 tau. Okay, your inductor will reach to a steady state condition, and then your answer will be 0.5 ampere, and this will be continuously flowing. So if you observe this expression, previously our focus on in initial chapter, we are either calculating this value, final value, or maybe possible we will calculate the rate of decrement or rate of increment only. But now we have obtained this expression. So maybe possible in exam, sometimes they may ask, you have to calculate the current value for, let us say, 0.01 second. Then you put the value of t equal to 0.01 second in this expression, you will get maybe possible some value over here. Maybe possible they may ask some another time, you may calculate that time and you can obtain this value. But if you put the different values of t in this particular expression, you can get this and you will get this plot. Okay, so I hope you find out this lectures helpful and you will be continue with us in next few lectures. Thank you.